In this video, we're going to continue to look at molecules with more than one chirality center, and we'll see how Fischer projections can be used to represent these. I've been telling you about how biomolecules are usually made as only a single stereoisomer. And yet, I pulled these structures out of a biology textbook, and they are showing these structures for these important biomolecules. So lactate, glucose, and galactose. Now, technically, these don't have any stereochemistry. These are just Lewis structures, which shows the connectivity, but this doesn't mean anything in terms of the stereochemistry. Sometimes the biology textbooks get it wrong. What they are trying to do is show Fischer projections. So these structures here are Fischer projections, and these definitely show stereochemistry. So by convention, we do not draw the carbons in the chain. We draw the chain vertically, and there is a specific meaning to the bonds that are horizontal and the bonds that are vertical. So here we have a generic Fischer projection, and what this means is all of the bonds on the horizontal are coming forward, and then all of the bonds on the vertical, these are either back or in the plane. So for this one, we would have X and Y are coming forward, A and B are going back behind the screen. Looking at glucose, we have all of these carbons. Now we do not draw the carbons. If we draw the carbons, it's ambiguous because really what we're drawing is a Lewis structure, even though we're trying to draw a Fischer projection. So we do not draw in the carbons. We draw it in with the carbon chain on the vertical, and then there is the specific meaning. So we can think of it as if all of these carbons are in the plane, and then this one would be going back, and this one would be going back. Now, if you actually built a model of this, this would have a curve to it. So we kind of have to pretend that we are flattening out the structure so that these can be in the plane, and then just the ones on the end are going back behind. Now, all of these are coming forward like this. Now, with a Fischer projection, because it is showing stereochemistry, then you can assign RS configuration to any of the chirality centers. So let's say we're interested in this carbon here. We need to remember that this hydrogen is coming forward, this OH is coming forward, and then this is going back. When we assign priorities, the oxygen will be priority 1, the hydrogen will be priority 4, and then we have a carbon and a carbon. The carbon on top is connected to oxygen, oxygen, hydrogen, because remember, double bonds count as it's connected to 2 oxygens, whereas this carbon is connected to oxygen, carbon, hydrogen. The oxygen-oxygen is higher priority than oxygen-carbon, so this is priority 2, and this is priority 3. Now going from 1 to 2 to 3, we are going counterclockwise, which is S, but because our lowest priority is coming forward, we would flip the assignment so that has the R configuration. So Fischer projections can be a very useful shorthand. It's a lot quicker to be able to just draw a cross rather than having to fill in the dash and wedge. But you need to remember the very specific meaning of the horizontal lines as well as the vertical lines. And you need to make sure that you are showing everything in the Fischer projection convention rather than just doing it halfway and accidentally drawing Lewis structures. So if we have a molecule such as 2-butanol, how do we draw that as a Fischer projection? Well, notice we have one chirality center, so we can draw this as a cross. And on top, we have the methyl group. On the bottom, we have our ethyl group because we are putting the chain, the longest chain, in the vertical. And then on the horizontal, we're going to have the OH group and the hydrogen. So one possibility is we have the H on the left, OH on the right, or we have the OH on the left and the H on the right. Please don't forget, if you are writing your OH on the left side, make sure you have the oxygen on the inside and then the hydrogen there. It's not correct to write it like this, so don't do that. So although I've drawn these very different from each other, they're supposed to be mirror images. All right, so we have the one chirality center, and the molecule 2-butanol can exist in this configuration or in this configuration. If you have a Fischer projection and you want to convert it to a dash wedge version, then remember that if this is the chirality center here, then we have our OH coming forward, our H coming forward, our ethyl is going back, and our methyl is going back. And this other one, we have the methyl and the ethyl, and coming forward is the OH, coming forward on the right side is the H. So whether we're looking at it this way or whether we're looking at it this way, we can see that we have a pair of enantiomers because these are mirror images that are not superimposable. If we look at butane 2,3-diol, now we have two chirality centers. So we can draw it like this, where here is a methyl group and a methyl group. We could have our OH on the left, H on the right, OH left, H right. And then we could have the mirror image where H's are on the left, OH on the right, and another methyl. We could have the methyl, OH on the left, and then OH on the right. And then the mirror image of that one would have the H on the left, OH on the right, H on the right bottom, OH on the left. So these are a pair of mirror images, and these are a pair of mirror images, but these are not mirror images. With this pair of mirror images, if we tried to slide this molecule over, then they would not line up on each other. If we tried to manipulate this, no matter what, these are not going to line up on each other. So what we have here is a pair of enantiomers. With these molecules, they are mirror images, but we also have a plane of symmetry in the molecule. And so what we have here is a meso compound. It has chirality centers, but overall it is a chiral because it has a plane of symmetry. So even though these are mirror images of each other, they are superimposable. Now what we're allowed to do is we can take this Fischer projection and we can rotate it 180 degrees in the plane of the paper. So let's imagine that we're doing it like this. We're rotating it this way. That's going to put this OH on top of this OH, for example. And so these molecules are superimposable, which means they are not isomers. It's just the same compound. So going from a structure to a Fischer projection, going from a Fischer projection to a dash wedge, or going from a dash wedge to a Fischer projection, these are all things that will take some practice. Now, are there limitations to Fischer projections? Well, over the last few chapters, we've been doing a lot with stereochemistry, different conformations, different configurations, and I've been encouraging you to manipulate molecules to be able to see them from different perspectives. Unfortunately, with Fischer projections, we're limited with what we can do. So for example, Let's say we are looking at this Fischer projection. If I wanted to flip it over like a pancake, so I'm just going to flip it horizontally, and then I rewrite it like this. Here's the CH2, CH3, here's the H and the OH. All right, this is another Fischer projection, so that's great. Except that this is not the same as this. The problem is that in a Fischer projection, this is coming forward and these are going back. If I flip it over, now these are going back and these are coming forward. But that's not what a Fischer projection says. So we are not allowed to move the Fischer projection out of the plane. So we cannot flip it over like a pancake. Here I said we could rotate it 180 degrees, and I encourage you to build a model, build another model, rotate it 180 degrees, and make sure that it gives you the same thing. So you can do this manipulation in the plane of the paper. Well, let's come back if we look at this structure. What if I wanted to rotate this, not 180 degrees, but just 90 degrees? So I want it to look like this. We have the OH and the methyl and the H and the ethyl group. But here we have the OH coming forward and these are going back. And yet, if this was the Fischer projection, this is going back and these are coming forward. So this is no longer the same molecule as what we started with. So you cannot do 90-degree rotations. You cannot flip the molecule. In other words, there's a lot of limitations when it comes to Fischer projections. Basically, I recommend if you have to do manipulations, convert your Fischer projection to a dash wedge and then do your manipulations on the dash wedge representation. Well, given the limitations with Fischer projections, we cannot really manipulate them. Why are Fischer projections useful? So here is a Fischer projection for D plus glucose. The plus refers to the direction of rotation of optical activity. D, we use D and L for certain biomolecules, and that actually specifies the orientation here, whether the H is on the left, OH right, or the other way. And then glucose is the name for this specific orientation of the OH groups. Now, if we use a Fischer projection, it is a shorthand. We're limited with what we can do to it, but what's the alternative? If we were instead to draw D plus glucose using a zigzag structure with dash and wedge for the OH and H, there's a lot of different options. So it can be difficult enough trying to remember which is D, which is the glucose, where are these OH groups. Imagine if you had to look at every single one of these and figure out, okay, this OH is forward and then this OH is back, but wait a minute, over here, this OH is back and then this OH is forward. So whenever you have molecules with a lot of chirality centers, two people can draw them very differently, which makes it hard to compare. So instead, by convention, Fischer projections are used. They're always drawn with the aldehyde up top and the alcohol on the bottom, which makes it even easier to be able to compare the different structures. So as we're working with small to medium-sized molecules, we're going to get a little bit of practice with Fischer projections. If you go on to study carbohydrates, then you're really going to get a lot of experience using Fischer projections because it is just very, very convenient.